Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Hello everyone. First, let's get a visualization for what is happening in this problem. So, we have a beam of electrons. We'll say that they're heading to the right, but our problem says that means they're heading horizontally from west to east. So we'll say that this is our westward direction, and this is our eastward direction. And we have a beam of electrons heading to the right. So we have a beam full of electrons all headed in a particular direction. Now, it also tells us that we have a particular component of the magnetic field that could affect these electrons, and that it's heading directly downward. So we have a component, the vertical component of the Earth's magnetic field, heading this way, and I'll represent it as a downward vector here. So if we go and adjust our coordinate system up here with west is left and east to the right, that means up and down are literally that. Up is towards the sky, down here is down towards the ground, and then into the page would be headed directly north, and out of the page is headed directly south. So, to answer the first question here, A, what is the direction of the magnetic force acting on these electrons? Well, we can just use our right-hand rule to figure this out. So for part A, let's put our pointer finger in the direction of the velocity of the electrons, and I said that they are heading to the right. So a vector here representing the direction of the velocity. So we'll have our pointer finger going this way, headed to the right, and then we want to put our middle finger headed down. That's going to be something like this right here. So velocity to the right, magnetic field heading down, and then when we do that with our hand, we see that our thumb is actually heading into the screen. Now, remember, so normally we'd say that the magnetic force would then be into the screen, but these are not positive charges that we're thinking about, these are negative charges, so we actually flip that result. So the magnetic force actually isn't heading into the screen, we flip that to the opposite, so we see that the way in which the electrons will be deflected because the magnetic force is actually out of the screen. And then in this case would be heading due south. So that is part A. We figured out which way the electrons are going to be deflected by thinking about what is the direction of the magnetic force acting on these electrons given by the right-hand rule. The next question is then, what is the acceleration that these electrons are going to be feeling from this magnetic force? Remember, if the magnetic force is the only thing we're considering to be acting on these electrons, then if we know the magnitude of the magnetic force and we know the mass of our electron, then we know the acceleration that it is feeling. And of course, we can look up the mass of an electron and we can figure out the magnitude of the magnetic force acting on it by considering our formula. Right? So the magnitude of the magnetic force is going to be given by the absolute value of the charge of our particle. In this case, it's an electron, so the electric charge. Multiply that by the speed of the electrons, multiply that by the magnitude of the magnetic field through which they are traveling, and then again, if we look at the direction of the velocity completely to the right, the direction of the magnetic field completely down, the angle between those two vectors is 90, and then our sine of 90 term can just go to 1. So we can leave our magnitude of magnetic force as simply as this product, but I can also write this out for clarity. Here we go. And of course, we have to follow through with dividing by the mass. So we can figure out the acceleration if we know the charge of our electrons, the speed with which they're traveling, the magnetic field through which they're traveling, and their mass. The only thing we don't know of this is the speed, but we are given the whole kinetic energy of the electron beam. So we can figure out on average what the speed of the electrons are given that kinetic energy. Right? So we're given this kinetic energy value, and we know that it's going to be related to the mass of the electron and its speed through 1/2 mv squared. So if we want to find the velocity, we just solve for it, and that's going to require us to multiply the 2 over, multiply it by the kinetic energy, divide by the mass of an electron, and then square root everything. Okay, Now, for simplicity and time, I'm not going to write out all the numbers in here. I'm just going to give you what the answer will be. To significant digits, we get a speed of about 7.26 times 10 to the 7 meters per second. That's about almost 25% of the speed of light. Not enough to consider relativity yet, but still pretty dang quick. Now, since we know that velocity, we can go ahead and use it back up in our problem up here to figure out the acceleration. So I'm going to plug in everything that I know. Now I know the charge of an electron is about 1.6 times 10 to the negative 19 coulombs. Magnitude, I'm taking away the negative. Multiply by the speed we just found through the kinetic energy, 6 times 10 to the 7 meters per second. Multiply that by the magnitude of the magnetic field, about 2 times 10 to the negative 5 teslas. And then, of course, we divide all of this by the mass of an electron, which is our small 911 times 10 to the negative 31 kilograms. Put that in our calculators, and in the end, we get our answer of a relatively large acceleration for these electrons of 2.55 times 10 to the 14 meters per second squared.